All right, probability posse. We are back with part two of day one of probability fundamentals. We are looking at the bottom of page 10 of the probability packet where we left off. And I was just about to tell you about a cool table that we can make that would help us with a bunch of these questions. Now we're kicking things up a notch. Now we're not just we're not just rolling one die. We're actually rolling, count them, two die. We're going to roll them. I got a 1 and a 3, and the outcome is going to be the sum of the pips on the two dice. I just love using that word. So it's going to be the sum each time. Make yourself a little T-chart here, maybe with the outcomes for the first die and the outcomes for the second die down the other side. So your outcomes are the numbers 1 through 6. So 1, we'll say 2, 3, 4, 5, and 6 go across the top horizontally, and then we're going to do the same thing vertically down. 1, 2, 3, 4, 5, 6. Space them out, 1, 2, 3, 4, 5, 6. Okay, now we've got a bunch of outcomes to write. This table is going to take a little while to write out, but it's going to be so worth it when it helps us answer all these questions that you see off to the side. So we've got to add the two dice. So it's going to be 1 plus 1 is 2, right? 2 and a 1 on the second one is a 3. 3 and a 1 is a 4. I'm noticing a pattern that if you add each of these to a 1, you get those numbers. And you're going to get 2, 3, 4, 5, 6, 7 going down as well. Can you continue the pattern? Continue to add the numbers on the two dice together. So 2 plus 2 is a 4, right? 3 plus 2, 5. 4 plus 2, 6, 7, 8. And you should get 5, 6, 7, 8 going down. Okay, we're working our way outward. Next up, we've got to add what's on the two dice. 3 plus a 3 is a 5. 3 plus a 4 is a 6, sorry. 3 plus 3 is 6. 4 plus 3 is 7, 8, and then 9. 6, 7, 8, 9. And then we've got down here, what am I up to? This will be 4 plus 4, so 8, 9, 10. 9, 10. And this will be 10, 11. And 11, and the highest value you could get when rolling two dice would be a 6 and a 6. That would be a 12. So another thing that we'll definitely be needing here is going to be the total number of outcomes. You take your pick. You could count up all of the entries in this chart, or let's think back to our counting principles that we learned in 11.1. Draw one blank for each dice, right? And write the total outcomes. You have 6 choices for what could happen on the first die and 6 total outcomes of what could happen on the second die. Multiply those together, you get 36 total outcomes. Keep this in mind. That should help us denominator-wise for these probabilities, since we talk about total number of outcomes as being the denominator. So I'm going to slide up a little bit. It says for part B, what's the probability you get at least 1 5? Now these questions are a little bit trickier than the ones where we're just rolling one die. We've got 2 to think about. At least 1 5 would be all these 6 possibilities, and actually all these 6 as well without double counting. Even 2 5s is okay. If you get this 10, you're in this case because at least 1 5 does cover 2 5s. So it should just be 11 of them. These 6 and these 1, 2, 3, 4, 5, being careful not to double count the 10. So I'll say 11 outcomes out of 36 total, 11 over 36. Part C, this question in part C might be the trickiest one out of the entire list, so we want to take this one carefully. It says probability out of these cases that you get at most 1 3. Well, at most 1 3 is a lot of cases. That's the probability of getting no 3s or 1 3. The only thing I think you're leaving out here is this one case. Where is it? 2 3s. I think this is the only outcome in the entire table of outcomes that doesn't involve either no 3s or 1 3 in it. So I think the easiest thing to do is not to add all these up. Let's subtract, right? You have 100% of the time you're going to get something in this list minus the one case, we'll say, out of 36. And this is called a complement, right? Minus the one case out of 36, that is that you get 2 3s that wouldn't be included here. So that is 35 of the cases out of 36. That is all of the outcomes besides the one that I circled here, the double 3s, okay? Probability of 1 7. 1 7 should be pretty quick, but wait a second, I'm being fooled. 1 7, you can't pull a fast one on me. No die is gonna read a 7 when you flip it. What do we put for an impossible event? Definitely put a 0 for that. Then a couple cases of sums, sum of 2, sum of 6. You know that if you go to the casino, I hope you don't go to the casino and gamble, right? But if you were to and you would play craps, they call a 7 a lucky number 7. Notice on this table there are a lot of 7s down a diagonal. There's more 7s in these outcomes of sums than any other number in the entire list. 7 has the most high odds of coming up when you roll 2 dice. Well, 6 has pretty high odds too, and there's some very unlikely outcomes, like a 2 and a 12. Snake eyes would be pretty unlikely, and double 6s would be pretty unlikely too. Sum of 2, I think that's only one case that you get snake eyes out of all the 36. Sum of 6, I think I can count up 5 of those. 1, 2, 3, 4, 5 times I saw a 6 in the list. So 6 over 36 gives you 1/6. You have a 1 in 6 chance of getting a sum of 6. There's a part G, and I want to add one to this, but how about part G? Sum is odd. I wonder if the answer we get for this is going to surprise you or not surprise you. Odd sums, 1, 2, 3, 4, 5, 6. I'm just counting the odds. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I probably could have guessed this one, that it was going to be half of these sums with 2 dice, 1 through 6, are going to be odd, and half of the outcomes are going to be even. So can you add a letter H at the bottom here? There's a question I wanted to ask, and it's probability of doubles. So I'm not talking about a specific sum here. I'm talking about what are the odds that the same number comes up on both dice. So doubles, I think in Monopoly, don't you get to go twice when you roll doubles, right? That's pretty cool. Doubles is going to be double 1s, double 2s, double 3s, double 4s, double 5s, double 6s. So that is 6 out of the 36 options. And again, you get a 1 in 6 chance. As we scroll to the next page, go ahead to page 11. You're going to see a lot of info about playing cards. Keep this in mind. I keep saying playing cards are going to come in handy for us as we move through the packet, but I actually want to save the info about playing cards for our next session. So let's skip 5 for a second. Just know that that info is there. And then for 6, the last thing I wanted to try with you is a really good challenge problem. And I like talking this one through because it's both difficult and thought-provoking, and, spoiler, it's going to tie in some of the same counting principles that we used in 11.1. We might see a permutation or a combination involved, and we'll combine that with probability in this question. This is when things continue to be really fun. It says a batch of, oh, now I'm going to get hungry, a batch of 48 chocolate chip cookies in number 6 has 8 cookies that are missing chocolate chips. So you know that for a fact, if 5 cookies are just randomly selected, like the cookies are baked and I just put my hand on the plate and I select them blindfolded, what's the probability, now this is pretty specific, that exactly 2 of them are missing chips? Think about this one. Maybe pause the video and see what you would think to do first, because I would love for you to brainstorm and see what you come up with, and I'll give you a hint. Combinations are going to help with this one. A fraction that's got multiple combinations, maybe on the top and the bottom. So let's see, can we solve this? You want to figure out up top the number of ways that this could occur, that 2 of them could be missing chips. On the bottom, you want the total number of ways or total number of outcomes that could happen. So up top, this is pretty specific. We want 2 to be missing chips. Does the order in which I pick up the cookies really matter? I don't think so. You're just counting how many are missing chips. So let's use combinations instead of permutations. We want 2 of them to be missing chips. Well, how many ways could we get 2 of these 8 that are missing chips? Let's go 8C2. This is the way to pick 2 that are missing chips. I actually prefer my cookies to have like 1 chip in them. For some reason, I just like the cookie part way better than the chips. Call me crazy. I also don't like the cream inside the Oreos, but that's a discussion for another day. But this is the way you can pick 2 that are missing chips out of 8 total. Well, you still are selecting 3 more cookies, and we have to account for that. That's going to give you more ways this could occur up top. So times and a combination for the 3, we need to pick 3 that have chips, that have chips in them, right? Okay, so the 3 that are there. And that is, we want to pick 3 out of how many in the batch do contain chips? Well, 8 of the 48 didn't have chips. The other 40 do have chips. So the 3 that have chips is going to be this combination. Pretty wild that we can use that to help with the number of ways this could occur. On the bottom, you have the total number of possible outcomes just for, in general, picking 5 cookies out of 48 cookies. Order doesn't matter. So you're going to do a 48C5 on the bottom. It's a little bit unexpected here. I'll be the first to admit that. But this should give you a good answer, and you're definitely going to want to use the calculator to help with these combinations. So I will slide over, and let's do up top, 8C2. So 8 math. And then probability combinations, we want the third option, C2. Enter. Okay, so you get 28 up top. Next to it, we want 40C3. This is going to make the number really big. So I'll just say times 40C3. And this way, it's already going to multiply it. It's just going to give me a huge number for the top of this fraction. 40C3. So 28, I'll just cross it out, times 40C3 gives you a huge number. It's going to be 276,640, like that. On the bottom, we need 48C5. 48, we want to divide this by 48 things, and we're picking 5 cookies out of the 48. Okay. Oof. Okay, so 1, we've got 1,712,304. This definitely reduces. I know for sure that at least a 2 goes into the top and bottom as a common factor. For a crazy fraction like this, even you hitting math frac in the calculator isn't going to do much good. 276,640 divided by, and then can I go up and grab it? 172,304. Enter. Even when I hit math, I'm going to try doing this the lazy man's way. Math frac should just leave this decimal a decimal. If you're going to give me a probability as a decimal, here's what I request. Can you give me at least 3 decimal places so that as a percentage, you've got a nearest tenth of a percent? We'll round this to 0.162. You have a 16.2% chance that this exact outcome could occur, exactly 2 that are missing chips. Makes me want to go up and eat some cookies. I hope you enjoy the rest of your day. Thanks for tuning in, and stay tuned for day 2. See ya.